this lesson, we're going to discuss types of graphical representations for frequency distributions. So essentially, we know that a frequency distribution is a table, and we're going to take that table and convert it or transform it into a graph. Now, if you don't know how to construct a frequency distribution, then I would recommend that you go ahead and you learn that first, because this lesson is solely going to focus on taking an already constructed frequency distribution and converting it into a graph. A histogram is a graphical representation of a frequency distribution. So as I said before, we're going to take a frequency distribution and we're going to take that data from that table and convert it into a picture. So our bars are going to represent the frequency per class, where the height of the bar is actually representing the frequency, and the width is going to represent the class limits or the class boundaries. So remember, our frequency distribution either has class limits or it has class boundaries, and then we have our actual frequency. That is when we're working with a grouped frequency distribution. So our bars, or the bins of the histogram, are going to represent the range of values that fall within that specific boundary. So let's look at this example. 20 people were surveyed where we measured their weight in kilograms and we recorded it on the table you see on your screen. So this table is essentially a data set, and each weight is a data value. So we have 20 data values in our data set. So we're going to take these data values and we're going to identify what type of data we're working with. We can see that we're working with continuous data. Why is it continuous? It's because we're working with measured weight. So we know we have continuous data. So ideally, we would come up with a grouped continuous frequency distribution. Now, like I said, I'm not going to show you how to construct a frequency distribution. Instead, I'm going to use the already constructed frequency distribution and go ahead and show you how to construct the histogram. This specific example is actually included in a previous video, so if you want to go ahead and check your work, or if you want to see how you construct this frequency distribution, then just click on the link above and you'll be directed to that video. Okay, so this is our frequency distribution for this data set. We see that we have 1, 2, 3, 4, 5, 6 classes. We seem to have a class width of 10, and we have our frequencies recorded. So just a quick insight into how we would interpret this table. What our frequency distribution is telling us is it's telling us how many people have a weight between these boundaries, where our lower boundary is included and the upper boundary is not included. What do I mean by this? I mean, when we're going through our data set and we're identifying the values that fall within this range, we're going to identify values that are greater than and equal to 36.5, but less than 46.5. So what we're doing is we're identifying values that are greater than and equal to our lower boundary, but less than our upper boundary. Okay? So if we had a value of 46.5 in our data set, it would fall into this class, because we know that the lower boundary is included, and it wouldn't fall into this class because the upper boundary isn't included. So 46.5 is not included. Okay, so now that we understand how to interpret this frequency distribution, all we're going to do is we're going to construct our histogram exactly as we described above. And there we have it. So as we can see, we have 1, 2, 3, 4, 5 classes because we only had frequencies for 5 classes. So we left out this class with a frequency of 0. And we can see that the bins, or the width of the bars, are giving us our class boundaries, and the height is giving us the specific frequency for that boundary. So as we can see, for our first boundary, we have a frequency of 4. Here we have a frequency of 5, 6, 3, and 2. Okay, and that corresponds to exactly what we have in our frequency distribution. And there you have it. Now you have a histogram. So you may be questioning, what's the point? You basically just take the exact same information and just put it into a picture. And well, that's the whole point. When you actually work in industry, this is going to be a significant part of your job. You're going to essentially be a translator. You're going to be communicating with people who do not have a statistical background. And so you want to take information and you want to translate it to them in the fastest and the easiest way for them to understand. And our brains actually interpret pictures or graphs much easier and faster than it would a table. So when you look at this histogram, I can very, very quickly see that most people weigh at least 56.5 but less than 66.5. Whereas if I look at the frequency table, it may take me a little longer to see that. So the whole point of this is we're essentially taking the same information, but we're just putting it into a format that's easier to interpret. So now that we understand that, let's move on to how you would actually be tested on this, or how we can actually use this histogram and determine probabilities. So let us assume that you're asked, what is the probability that a randomly drawn person from this dataset will weigh at least 56.5 kilograms, but less than 86.5? So the most important thing from this question is you want to pay attention to these last two lines, because this is giving us the range of values that we're interested in. Now the term at least means that we're looking for values that are greater than or equal to 56.5. At least, so it must be 56.5 or more. Okay, so we know that we're looking for values that are greater than or equal to 56.5, and the last line says less than 86.5. Now the reason why I say this is the most important thing you want to understand is because actually determining the probability just simply comes down to plugging in values into a formula. So that's not the hard part. The hard part is actually understanding the range of values you're working with and identifying the frequencies that correspond to those range of values. So as we said, we're interested in weights that are greater than and equal to 56.5 but less than 86.5. Okay, so let's look at our histogram. Now remember how we read this. We read this as greater than and equal to the lower boundary, but less than the upper boundary. So you can clearly see what weights fall within which bars. Okay, now we want a weight that is at least 56.5. So we're going to go from the left and we're going to identify the first bar that includes 56.5. Going from the left, we see that it is the third bar. So the third bar is the first bar that includes 56.5. Remember, this bar doesn't. It's just less than. There's no equality sign here. So this line at the bottom means equality. There's no equality sign here, so it is not included. Okay, so we're going to go sequentially, and we're going to stop at the bar just before the bar that includes 86.5. So we can see that we're going to stop at this bar. Because if we go into the next bar, now we're including 86.5 and we don't want that. So what we've just identified is our bars of interest. So the bars of interest are these two bars. Now the reason we need to do this is because we need to identify the frequencies, because we're going to use those frequencies to calculate the probability. The formula we're going to use is the summation of the frequencies divided by our total number of data values, or n. However, we're only going to sum the frequencies that correspond to the bars of interest. So I've just loosely put this formula here. If you were to use this formula formally exactly as it is, you would get an answer of 1. Because using this formula, we would sum up every single frequency and we would divide it by n. But we know that if we sum up all the frequencies, we're going to get n, and n divided by n is 1. So it's important that you know that you're only going to sum up the frequencies that correspond to the bars of interest. And that is why we went through this process of identifying our range and then identifying the bars of interest. So in this particular case, we're interested in the frequencies 6 and 3. So we're going to say 6 plus 3 divided by 20, which gives us an answer of 0.45. And what this tells us is that there is a 45% probability. You could also just say 0.45. Remember, 45% is 45 over 100. So there is a 45% probability that a randomly drawn person will weigh at least 56.5 kilograms, but less than 86.5 kilograms. So what this question is telling us, I'm just going to put it into perspective for you. if we were to write down all the weights of the people from our data set on individual pieces of paper, so we have 20 pieces of paper, and we put it into a bag, and then if we were to put our hand into this bag and just randomly, blindly pull out a piece of paper, what we're saying is that there is a 45% chance that the weight on that piece of paper is going to be at least 56.5 kilograms and less than 86.5 kilograms. Moving on to the next graphical representation, we're going to look at a frequency polygon. Now, for the frequency polygon, we're going to actually work with the class midpoints and we're going to plot them against the frequency. So if you don't know how to calculate class midpoints, I'm going to show you how to do it. And essentially what we're doing, you can very loosely think of it as constructing a line graph. I'm going to show you how it differentiates from a line graph. However, if you know how to construct a line graph, then this shouldn't be too difficult for you. All right, so here we have our frequency distribution. We're working with the same example. And how do we in fact come up with midpoints? And it's really quite simple. We're just going to sum the lower boundary plus the upper boundary and we divide it by 2. And if you had to think about it, if you are measuring something that's, let's say, 30 centimeters, and you wanted to find the midpoint, you would say 30 divided by 2. But what did you just do? You actually, in fact, took your starting point, which is 0, and you said 0 plus 30 divided by 2. So that's exactly what we're doing here, and we're going to go ahead and we're going to just sum that up, divided by 2, and come up with our midpoints. Okay, so there we have our midpoints. Now, this is where it changes a little bit. In order to construct a frequency polygon, you need to include 2 additional midpoints. And the reason we include these 2 additional midpoints over and above all the midpoints we have is because we want to anchor our graph to the x-axis. Now, I'll explain why we do that, but let's first discuss how we in fact come up with these midpoints. So if you know what your class width is, then this is really easy. But if you were just given a frequency distribution and told to construct a frequency polygon, then you would need to determine what that is. The class width or just the difference between the midpoints, they're going to be the same. So you can just take any 2 consecutive midpoints and you would take the absolute value of the difference. And whatever you get as the answer is going to be used to construct these 2 new midpoints. So if we were to take just any 2 midpoints, consecutive midpoints, and we were to find the absolute value of the difference between them, we would see that there's a difference of 10. So it's quite clear. If you just look at from the first midpoint, we are incrementing by 10 to get to the next midpoint. So if we were to do that, we would get midpoints of 31.5 and 101.5. And we just give this a frequency of 0, because remember, we want to anchor to the x-axis. If you don't understand what I mean, you're going to see it when we actually come up with this frequency polygon. So our frequency is going to be our y coordinates and our midpoints are going to be our x coordinates. So it's pretty straightforward from here. This is exactly what you probably did in high school. You're going to use these points, you're going to plot it, and you're just going to join this using a line. As you can see, the points 31.5 and 101.5 are in fact pulling the graph down to meet the x-axis, so it is anchoring our graph. And the reason that we do this is because it makes it easier to see the shape. If we did not do this, then our graph would likely end over here and it would end over here, and then it would just look like a weird line. Whereas when we anchor it, we can fully see the shape of the data. And there you have it. That's your frequency polygon. The last graphical representation that we're going to look at is the less than ogive curve. Now, the less than ogive curve is actually going to make use of something called cumulative frequencies, and it's only going to use the upper boundaries. So we're not going to use lower boundaries, we're only going to use the upper boundaries from our frequency distribution. A less than ogive curve is going to tell us how many data values, so in our case, how many weights lie below a particular data value, so below a particular weight in a data set. So ideally, we need to work with a cumulative frequency distribution. If you don't know what a cumulative frequency distribution is, I'm going to actually explain it, because as long as you know how to construct a frequency distribution, then all you need to do is you need to add on a calculated column called cumulative frequency, and that's going to make it a cumulative frequency distribution. Okay, so we're working with that same example just for simplicity, and we've added on a column called cumulative. So this is exactly what you would do if you were told to construct a cumulative frequency distribution. You would first construct the frequency distribution, and then you would add on a column called cumulative frequency. Now, a cumulative frequency is essentially a sum of frequencies. If we're looking at the first row, then the cumulative frequency is going to be whatever the frequency is for that row plus all the previous frequencies. So we can see that for our first row, our cumulative frequency is going to always equal to the frequency because there are no previous frequencies. Okay, so keeping that in mind, for the second row, our cumulative frequency will be 4 plus 5. For the third row, it's going to be 4 plus 5 plus 6. For the fourth row, it's going to be 4 plus 5 plus 6 plus 3. And for the final row, it's going to be 4 plus 5 plus 6 plus 3 plus 2. We know that our cumulative frequency for the final row must always equal to the number of data values in our data set. Why is that? It's because we've added all the frequencies, and we know that our frequencies must sum up to all the data values. Okay, so going ahead and doing that, we have our cumulative frequencies of 4, 9, 15, 18, and, of course, 20. So we're going to do something similar for the ogive curve that we did previously. Okay, so we've introduced another row, so that means we're going to introduce an additional upper boundary and an additional cumulative frequency. So I've left the frequency column there, however, we do not need it. For a less than ogive curve, we're only interested in the upper boundaries and the cumulative frequencies. So we're going to do the exact same thing. We're going to identify what's the difference between any two consecutive upper boundaries. Obviously, the absolute value of that because we want a positive number. And then we're simply going to take 46.5, subtract that number to get the upper boundary that would come before 46.5. So we're going to subtract 10 and we get an upper boundary of 36.5 and we give it a cumulative frequency of 0. Okay, so using the upper boundaries and our cumulative frequencies, where the upper boundaries are our x coordinates and the cumulative frequencies are our y coordinates, we're going to construct our ogive curve. So as you can see on your screen, we have our upper boundaries on the x-axis and our cumulative frequencies on the y-axis. And we can see that the upper boundary of 36.5 that we introduced is anchoring our graph to the x-axis. So let us interpret this graph. We can see that 4 people have a weight less than 46.5. Remember, it's less than, not less than and equal to. 9 people have a weight less than 56.5. 15 people have a weight less than 66.5. 18 people have a weight less than 86.5. And of course, 20 people, so everybody in this data set, has a weight less than 96.5. Now, why wouldn't we anchor the graph on the right-hand side as well? Why did we only anchor it on the left? Well, think about what you're doing. By anchoring it on the left, we can interpret that point as there are no people who have a weight less than 36.5. And we know that to be true because that boundary doesn't exist in our data set, so there's no data values for that boundary. So what we're saying is that there's nobody in our data set that has a weight less than 36.5. So anchoring the graph to our x-axis on the left-hand side makes sense. However, if we were to anchor this on the right-hand side, then what we would have been doing is we would have to say that no people, because remember it's on the x-axis, so we're going to have a frequency of 0. We're going to say no people have a weight less than 106.5. But we know that 20 people should have a weight less than that, because if 20 people have a weight less than 96.5, then definitely 20 people should have a weight less than 106.5. However, if we anchor the graph, then it's going to give us information that does not make sense. So when you're working with anything, just try and understand what you're doing. Because if you try and memorize things, it's going to become a lot. However, if you understand what you're doing and it makes sense to you, it's going to be a lot easier for you to retain that information and actually produce that information when you need to. That brings us to the end of the lesson. Thank you so much for watching. If this video has helped you in any way, kindly like and subscribe and turn on that notification bell to keep learning.